know how radar is work when it comes to detecting other aircraft, right? From air to combat. So now you guys are designed to both get a model of the other aircraft, you can target specific parts of it. I mean, that's a good question. Since rounds do that anyway, like it only takes two, 3 or 4 hits, even less nowadays because of how big the cannons are. Um, like the rounds are like this big, sometimes even this big. Yeah, there's thousands that fire in a minute, but they're not used for air combat anymore because it's too far. It's like using a knife in a gunfight. Like if it ever comes down to that, the gun's there, but it's mainly air-to-air missile. You used up everything else.
All right, good morning. Okay, let's try that again. Good morning. Okay, so how was the exam?
It was hard, but it was like you can get through it. It was like exam two.
No surprise, right? There shouldn't have been anything that was surprising. Good, good, good. Okay, so as usual, I'll send out the Scantrons this morning. Judging by how fast they work in the past, I'll probably get the results back this afternoon, and you should expect to see your score sometime early next week, if you choose to do so. Let's take a look at the calendar a little bit. Okay, so today we're going to cover section 5.3. Remember, Monday, no lecture. Tuesday, no recitation. And of course, Wednesday through Sunday, your Thanksgiving break. We'll come back for one more week, 3 more lessons, and then we'll start reviewing for the final. So we don't have a whole lot of time after we come back from the break. We're very close to the end. Okay, so we're going to be looking at section 5.3. The topic is on the fundamental theorem of calculus. This is where we tie things together, how derivatives and antiderivatives are connected and how they're connected to the slope, the area, and all those things. So first, remember, the definite integral of f of x from x is equal to a to x is equal to b represents the area under the function f of x from x is equal to a to x is equal to b. Okay, so that little segment, that region there, that's the area that would be given by this quantity right here. Now we're going to make this b here not fixed anymore. So let's look at this function here. We'll call this function g of x. And we're going to start from x is equal to a fixed location. But we don't specify the end, right end here. The function we're dealing with is still the same function. Notice I changed the variable to a t here. That's to avoid duplicating that x. We don't want to use x here and then x here and here again. T is just a different variable representing exactly the same thing that we have been looking at. So this is still going to give us the area under this function, f of t, from x is equal to a to an unspecified x. You can think of this as the area accumulated so far up to whatever x you want to specify later. All right, so this area is going to be a function of x. Once I decide what x is going to be, then I know the area. But until I decide that, that's just going to be a function of x. For a function of x, that means it has a derivative. So how can we find the derivative of this thing? Then that's the first part of the problem we'll investigate. Okay? In other words, what is the rate of change of the area accumulation of this thing? Once we find out the derivative of that, and then we know how to find the rate of change of the accumulated area. To find that, let's revisit the very, very first definition of derivative that we saw. Okay, that's the very, very first definition of derivative, just using the limit of the difference quotient. G of x plus h is the area accumulated under the function f from a up to x plus h. G of x is area accumulated from a up to x. And it's very difficult to deal with these things in their present form. So let's sketch what they look like, and then we're going to find a way to find out what the difference is. We need the difference of these two things on the top of that quotient. Okay, so let's sketch it out. Let's say this is a, and this is x plus h. So this one I'm shading in green is representing this one. So the green shaded region. The one below it, area accumulated from A up to X. Let's say X is right here, just a little bit before that. And I'll use red for that. No, I'll use purple. I have purple today, so I'm going to use that. Okay, then the difference between the two, if you subtract the small one from the big one, the difference is this red part. Okay, so the numerator of that quotient is the red region. Okay, everybody see that? You got a big one, you got a small one. Take the small one away. What's left is the difference, is the representing the top. Now we still don't know what that is, but we know we can put a rectangle inside that. So let me bring that out. We know from last time, we can think of this as being approximated by a rectangle using the left or the right endpoint of the interval as the height, right? And so we know this thing is, the difference can be approximated as a rectangle with a width of h and height of f of x. Yeah. Right. When h approaches 0, the approximation becomes better. Right? So that's the idea here. And we have a limit, and that's going to eventually give us that. Okay, so then this difference quotient right here, because h is becoming so small, the top here, this guy, is a rectangle of width h and height f of x. So that's got area equal to height times the width. Dividing by our h downstairs, those go away. And finally, when h goes to 0, f of x doesn't care. So we still get f of x as the limit. Okay, so let me write on the next page what this is telling us. Okay. So all we did here is using a limit definition, using the interpretation, the area interpretation, to come up with an approximation of the difference in area. But the approximation is very, very good once h goes to tiny, tiny number. In the limit, when h approaches 0, the approximation becomes exact, just like when we use lots and lots of Riemann sum rectangles to get that area, the whole area. Okay, so what we found on the last page. So we see that if the function g of x is defined as the area from x equal to a up to some other x, then the derivative is equal to f of x. In other words, we can think of this as the derivative of this integral right here, as equaling whatever the function that's bounding the top of the region. The rate of the change of the area underneath the curve is equal to the curve itself. This result right here is called a fundamental theorem of calculus. And it's part 1 of that theorem. I'll abbreviate this as FTC1 from this point on. The first part of the fundamental theorem of calculus. The important thing here is that it establishes a connection between integration, accumulating area, and differentiation, finding the slope of something. The slope of something and the accumulation of area, now we can see, is somehow tied together depending on what the functions look like. Show you some examples to make this more concrete. Let's say g of x tells us the area under the function cosine of pi t, accumulated from 0 up to some unspecified x. Okay, so there's my cosine curve, and wherever you want to end, let's say x is right here. And this quantity right here will be representing that shaded region. As you move x around, how fast that accumulated area changes is given by the derivative. The derivative of this according to fundamental theorem of calculus we saw above, the derivative of an integration turns out to be whatever the function bounding the region above. So it's equal to f of x. What is f? F is right here. Cosine of pi x. That tells you that what the curve is doing on the top determines how fast the area is accumulated. If you state it that way, it seems very obvious. But the mathematics behind that took a little bit of work to actually show that's the case. Any question on this part? Okay, now there are a couple things we've got to look out for when we use the first part of the theorem. Fundamental theorem of calculus part 1, again written here, only only works if x is the upper limit of integration. We want x to only works if x is representing the right end of the accumulation of the area. So that's called the upper limit of integration. Well, a here is the lower limit of integration. And notice, by the way, it doesn't matter what a is equal to. Whatever a is equal to, as long as it is a constant, the result is the same. Now, if you don't have x on the top, we can use a property of definite integral to fix that. Let's say if they are reversed. If I somehow have x down here but a on the right, we can reverse the two of them. But when we do that, we have to flip the sign of everything. We put a negative in front of that. Okay? You can flip the two, you can interchange the two anytime you want, but each time you do an interchange here, you have to change the sign from plus to minus, minus to plus. If you can do that, then this can be used again. For example, sometimes it becomes a little bit difficult to interpret that in terms of an area, but the mathematics doesn't change. We can still use the rules we have and apply the theorem. So even if you can't visualize what this area looks like or what it's really representing in terms of an area, it doesn't really matter. Okay, we can interchange the two, flip the sign. Then the derivative, according to the first part of the theorem, the derivative and the integration, basically they cancel each other out. So this goes away once we take the derivative. All we got left is what's inside. And we change that t to an x, because we want this to be a function of x. Questions? Okay, now another little bit of a wrinkle. What if that x is not just x? But some other functions of x. For example, let's say this thing is y. We'll call it y. 2 to e to the 3x of sine squared of 5t dt. This means that we're accumulating the area under this curve starting from 2 to some other number determined from some other function. We are looking for the rate of change of y with respect to x, of course. Okay? And we can handle this using chain rule. Let's let this e to the 3x be something else. Call that u for the moment. So this y here is 2 up to u sine squared 5t dt. So it's a function of u, but u in turn is a function of x. We got an intermediate variable in u here. We know from chain rule, the derivative of dy dx is equal to dy du times du dx. Right? That's a basic chain rule that we saw. We've used many, many times. It still applies. It doesn't matter what the function looks like. We know how to differentiate it. So the chain rule, of course, applies easily. The first part is this. Take the derivative of this with respect to u. And that's just the first part, the fundamental theorem of calculus. Okay? The first part, dy du, this will become sine squared 5u. From the first part of the fundamental theorem, right? The differentiation and integration cancel. We keep what's inside here, change t to the variable. This time the variable is u. So that's the first part. Second part, du dx. This is u. The derivative of u is 3 times e to the 3x. Now that's left here to do here is to clean this thing up a little bit. We don't want the u to stay in here, so let's get u back out. Let's write this as sine squared of 5 times u. Right, this guy is u times, let me put a 3 up front here. 3 from this e to the x back here. Okay. So that is the derivative of this. Okay, questions? Okay, so the first part of the theorem establishes a connection between integration and differentiation. The second part is the one we actually use more often, allows us to find the area precisely. Riemann sum only gives us an approximation. can be a good approximation, but it's never exact. If we want to find the area under a curve from A to B exactly, then that's what the second part of the theorem tells us. Let me write it down here, and then we can try to reason why this works. The second part says, if you want to find the area accumulated from A to B under the curve f of x, it is equal to capital F, I'll explain what that is in a little bit, at the right end minus capital F at the left end. And capital F is just an antiderivative of f. In other words, capital F prime is lowercase f. Okay, so this is actually a very useful result. If you could find the antiderivative of whatever the function bounding the top is, all you need to do is what it is at the right end, subtract it away what it is at the left end. Okay, so why does this work? Think about what f could represent. Suppose f of x is the velocity. Then we know from last time that the area accumulated under the velocity can be used to represent the total displacement. Which can represent a distance. Let's suppose it's the distance. Right? If you want to find out how much distance you have traveled, then all you need to know is where you started and where you ended. Distance is what the difference between the end location and the start location. Okay? So the end location if lowercase f of x, then the integration of that gives you if you undo the derivative, you get distance. Right? So capital F represents undoing one layer of differentiation, giving you back the position. This is the position at B. And this right here is the position at A. Okay, if I tell you I left Lafayette and I went to Indianapolis, how much distance did I travel? How I got there, my velocity on the way there is completely irrelevant. All you need to know is to subtract the distance between here and Indianapolis. How I got there on the way, completely irrelevant as far as my total displacement is concerned. So that's what this is saying. If you have a function right here, once you undo one layer of derivative, then find out what happens at the endpoints, take the difference, and that's what you want. That will represent the total distance. If you think about this way right here, the way I've written down here, then this will make sense. And then this theorem just extrapolate that and say, okay, it doesn't have to be distance, but the same principle applies. This result is still the same, no matter what lowercase f can represent. Okay, does that make sense? Yep. All right. Okay, let's try this on something. Let's first try on something that we can actually verify independently, as another check that the theorem does work. Let's find the area under 2x from 0 to 3. Let's first use basic geometry to see what we should be getting. Then let's compare to what the theorem tells us. Okay, so that thing is representing the area of this triangle under a line with a slope of 2, starting at 0, ending at 3. If y is 2x, then when x is equal to 3, y is equal to 6. So this is a triangle with a height of 6 and a base of 3, right? So the area, 1/2 times base times height, gives me 9. That's what I should be getting. When we apply the fundamental theorem of calculus, we better get the same thing. So let's do that. Okay, so if 2x is this lower case, then what would capital F be? What happens if we undo one layer of differentiation? What do we get? What function has a derivative of 2x? X squared, right. And what else? Right, it's x squared plus any constant. Okay, according to FTC2, that result is equal to this. Okay, capital F at the right end minus what it is at the left end. So what do we get? We get 3 squared plus c minus 0 squared plus c. At the end, we get 9 plus c minus c, and we get a 9. As it should be, right? As it should be. So we verify that we get what we should be getting. Note C is gone. And the answer is a number. Now, because we know C is always going to disappear, when we find the antiderivative in the future, we could just drop the C for the purpose of finding the area. We know it's always going to disappear. We often use a slightly shorter notation to represent all of this stuff. Usually you'll see people write it this way, within the square brackets of capital F, like that, or capital F with a straight line right here, A, B. All of these things are just representing the antiderivative of this thing at B minus what it is at A. So you see these two notations quite often. In the textbook, it uses both of these. When you see them, just remember they represent the difference between the two functions, the function evaluated at the right and then the end. Okay, let's check out this next one. Let's look at the area of the same function, 2x. But this time, we're going to start at -2 and end at 0. When we say area under something, what we really mean in general is the area bounded between that function and the x-axis. Okay? So this thing right here is representing this, the area of that line bounded between that line and the x-axis. In this portion right here, the x-axis is above the curve. So the area is actually this triangle right here. Let's see what we get when we apply FTC2. We know the antiderivative is x squared. Let's use the short notation we just learned. Okay, from the bottom here. This is representing what x squared is at 0. Minus what x squared is at -2. Okay, so you're putting this thing into here, and then you get that. And then, after that, you put this thing in here for x, and then you get this. And what do we get? We get 0 minus 4. We get -4. If you look at from a geometry point of view, the area is 1/2 base times height, and we get a 4. So here's the thing, we got to be careful. If the region happens to be below the x-axis, when we calculate the area from fundamental theorem of calculus, we actually get a negative area. The area is negative if the region is below x-axis. The number still tells us what the area should be, but we actually end up getting a negative number. That's because, remember, this comes from a bunch of little rectangles from Riemann sum. If this thing is below the x-axis, the height of each rectangle is negative. So each rectangle has a negative area. In the end, we end up getting this. Yes? It will be 0, because we would have half of the area negative, the other half being positive. Right. So from a geometry point of view, that doesn't make too much sense. But from the integration and Riemann sum consequence, that's what we end up getting. That means that we have two equal halves, two areas of equal size, but one below, one above. A net area ends up being a negative. Yeah, we'll deal with that complication the week after we come back. But you're right. If you want to find the total area, you need to know when the sign gets switched. So that's a little bit complicated. But if you know what the curve looks like, that's not too hard to do. All right, let's do a few more examples to get used to this thing here. Let's try this. find the area accumulated between this thing from x and the x-axis from 1 to 9. First thing we got to do here is we can deal with x to the n and simple elementary functions like sine, cosine, and e. We can deal with those things, but we can't deal with a rational function like that just yet. So let's rewrite this as a combination of x to the n. There's only one thing downstairs, so I can divide each individual term on the top by that same denominator. X to the first over x to the 1/2 is x to the 1/2. Minus 1 over x to the 1/2, that's x to the negative 1/2. Okay, now we integrate this stuff. Find out what gave us this derivative. Just do the power rule. Add 1 to the existing power divided by the new power. Same thing here. Add 1 to the existing power divided by the new power. And then whatever this turns out to be, we plug in x is equal to 9, find out what it is, subtract away what we get when x is equal to 1. Let's clean this up a little bit. It's at 3/2 downstairs. The reciprocal is 2/3. That's a positive 1/2 up. 1/2 downstairs, reciprocal is 2. So that's much easier to deal with. Okay, so we get 2 over 3. Now we plug in 9. Subtract away what happens when we plug in 1 for x. Okay, what's left here is simply to calculate this stuff. 9 to the 3/2 is 27. 9 to the 1/2 is 3. 3 times 2 is 6. Minus 2 over 3 minus 2. So that's an 18, right? 18 minus 6 minus 2 over 3 plus 2. In the end, we get 40 over 3. Okay, this 40 over 3, be careful. Remember, if any portion of this thing lies below the x-axis, that portion would have a negative area. The fact that we get 40 over 3 means that most of this thing is above the x-axis. There may be portions that's below, but the fact that overall net is a positive means we have more above the axis than below x-axis part to that whole region. Okay, let's do one more. Let's find the area accumulated between 2 over x squared plus 1 and the x-axis from minus 1 to 1. First thing that's sometimes useful is this. Let me show you. This, of course, means 2 times 1 over x squared plus 1. If you ever see a constant multiplying to a function, that constant can actually come out of the integration. Only if it's being multiplied. If it's added or subtracted, you cannot move that constant. But you cannot do that for subtraction or addition. If this were 1 over x squared plus 1, that plus 1 has to stay. But it's 1 over x squared times 2. That times 2 can be moved in or out depending on what you want to do. So there's my 2. Okay. Now, who can tell me what the antiderivative of 1 over x squared plus 1 is? Arctan, good. That's one of the special functions that we don't normally deal with, but it's an inverse trig function. You're right. It's an inverse trig of x. Minus 1 and 1. Okay? Notice that 2 is still there. So now we plug in 1 for that. We get inverse tangent of 1 minus inverse tangent of negative 1. What's the inverse tangent of 1? What angle has a tangent of 1? Pi over 4, right. What about inverse tangent of minus 1? What angle has a tangent of negative 1 in the fourth quadrant? Negative pi over 4. So we get 2 times pi over 2. We get a pi. Okay, that pi is a number, fine. But what's amazing about this result is if you graph this function, it looks kind of like a bell curve. So what we're saying is that this area under that bell-like shape from minus 1 to 1 has an area of pi. We often associate pi with circles. This thing clearly is not a circle, yet this funny-looking shape, this region right here, has exactly the same area as a circle with a radius of 1. So that's a very interesting result that actually when it first came out, was pretty unexpected. Okay, that's it for today. Remember, no class. We don't have this class on Monday. You may have other classes, I don't know. And there's no recitation Tuesday either. So the next time I'll see you is the Monday after the break. Have a good break. See you the Monday after.
plotting against